And welcome to the 54th Surface Ventures keynote webinar. It'd be great for you all to say hello in the chat. Tell us where you're joining from. Hello, Wolfram. Good to have you here with us. I'm sure more people will be typing any moment. My name is Dr. Sam McMaster, and I'm the content manager here at Surface Ventures. We are a non-profit organization, and our mission is to provide world-class surface and material science education for both academia and industry. Today, it's my pleasure to introduce Professor Ben Beake of Micromaterials. After postdoctoral study at Hull, Nottingham, and UMass in 1999, Ben joined Micromaterials, where he has been Director of Materials Research since 2006. He's a fellow of the Institute of Materials, Minerals, and Mining, and a past chairman of the Institute of Physics Tribology Group. Is currently a visiting professor at Manchester Metropolitan University and the Universities of Leeds and Huddersfield. He's very active in collaborative research and with other nanotest users, with over 175 published papers, particularly in developing nanomechanical test methods and applying them to study mechanical and tribological properties of thin films and coatings. We want to say thank you, of course, to our partner today, Micromaterials. Ben will be speaking a little bit as well about the strategic partnership with Artec Instruments, which some of you may have seen on LinkedIn and various social media to find out more about this today. We'll also be releasing some poll questions and handouts from Micromaterials at the event. I'll be highlighting those in the chat when they are available. Okay, so once we begin the talk, please do, whether it be anything instrumentation based or about the content of the talk, please type your questions into the chat. I will mark them for the Q&A, which we will get to following Ben's talks today. We're planning to go for around 60 minutes in total. We'll be sharing a link for your attendance certificates later in the event. That will be at the beginning of the Q&A session for anyone asking, so they will be there. Once you have your certificate, it'd be great for you to post and tag us on LinkedIn after the event and spread the word about what we do. So without further ado, let's welcome Ben to the stage. I'll get the slides up. Wonderful. Welcome, Ben.
Hi, Sam. So we were just chatting about the connection being perfect. My connection dropped out. So
oh dear. Well, hopefully that's it fine now. So there we go. You should have your slides.
Yeah, so where's
brilliant. Okay, stage over to you.
Thank you very much, Sam. Okay, so welcome everybody. So this is a very general presentation about some of the applications about using nanomechanical and tribological testing in biomaterials research. So what sort of things have I got in mind? Well, you can kind of split things into two areas. On the left, you have designing improved total joint replacements, hip replacements. So you have very much around the biomechanics, biomedical engineering, and on the right, you can also learn from nature to develop damage tolerant materials. So very much sort of biomimetic type approach. So I'm going to try and give a few examples of these type of research areas in the presentation. So I will very, very briefly introduce nanomechanics if people are not aware of what it is as a test technique. Then I will give a little dive into time-dependent deformation, and that will then lead into a short case study. So thank you very much to Professor Jason Zhang from Birmingham University for providing some slides for that. Then I'll talk a little bit about strain rate sensitive behavior with some examples, again, mostly from the US there. And then I will finish up with some examples of tribological testing at small scale and show how that can give us useful information. So micromaterials are primarily a manufacturer of precision instrumentation for nanomechanics. We also have activities in contract R&D, and also, as you see on the right, we also disseminate best practice through a range of technical publications and books and things like that. So nanomechanics is really all around trying to design small-scale tests to solve big problems. Characterizing the mechanical properties of materials at small scale, but also can be quite critical, and particularly for these sort of biomaterials under the relevant environmental conditions, be they of environment, temperature, moisture level, could be strain rate, and also to try and simulate those contact conditions in our testing. And that allows us then to, and our users to develop an improved understanding of how these materials behave under these conditions, and therefore to design better materials. So the work I'm going to be describing today is all done from various different groups on Nanotest Vantage systems. So those that don't know, Nanotest Vantage is a nanomechanical test platform. It's multifunctional. It has capability for a range of different small-scale mechanical tests: indentation, scratch, wear, fretting, impact. And these can be done at sort of nano and micro scales with different loading heads. And also, as I alluded to, different environments, different temperatures, different moisture levels. And in some cases, you can add additional information by multi-sensing test techniques that really allows you to understand with these multiple signals what's going on in these different contact situations. So for those that don't know, nano indentation is essentially a very small scale hardness test. We're applying a load to, or a force to, a very sharp point, and then we indenting into a material, and there's some penetration, and then as we unload, there's some partial recovery, and contact mechanics is applied to that unloading slope to determine primarily the hardness and elastic modules, but there's also a range of other information you can get over these type of tests. So this example here is just is an example on a fused silica reference sample. So fused silica is mechanically isotropic. So if you indent it at different positions, you should get the same behavior, and that makes it very, very useful to as a reference sample. So biomaterials, however, are inherently more complex. So they are mechanically heterogeneous at different length scales, typically. So here's an example about how we can use the sensitivity of the test techniques, so the ability to put very small indentations very close together to pull out some of this very localized mechanical property information. So there's some examples here where the instrument has been used, in this case by a group in, I think, AGH in Poland, to show how this seashell essentially has calcite crystals with different crystallographic orientations, and these orientations influence the relative proportions of slip and twinning and cleavage that occur. And so you can pull out differences in this and understand how that builds into the toughening mechanisms that these protective armor, these mollusks have. And you can then, once you have this information, then maybe you can use it to design better, that knowledge to design better materials. So it's another example in this case of mapping, again, a small volume. So this case, it happens, this is not a bio application by any stretch. This is a high temperature test map into a novel aluminium alloy design for high temperature performance and additive manufacture processing. And this map and things like this are designed to uncover these microstructure mechanical properties performance relationships at high temperature, and then to use that to design better performing additive manufactured alloys for these applications. So what you can see here is 1600 indents. They're all the same depth. They're spaced 1 micron apart, so the geometry of the probe limits how many you can do. And what you can see on the left there is essentially a multi-phase material with lots of features of through that structure of high hardness. But you can see on the right that it's a slightly more smeared out pattern when you come to the elastic modulus in the material. So if we think for a moment why that might be, And again, I'm come from a coatings background, so I think that, you know, it's easier to think for me in terms of these type of things, but you can think very much of a multi-scale material, and also think of the different length scales involved when we're doing for the elastic and the plastic stress field. So ISO 14577 part 4 shows this very nicely. So if we wanted the hardness of a thin film on a less hard substrate, essentially, so that you need to do a sufficiently small indentation and that plastic stress field remains within the coating. And that will, if you do those, enough of those, you get the reliable values for the hardness of the coating, provided you've got full plasticity. On the right is the associated elastic field shown schematically for the same sized indent. And you can see it's a much bigger field, so it's a much more far field effect. And what that's telling you essentially is if you then, that your elastic information is coming from further into the structure. So ISO 14577 tells you, gives you a way around that, where you can do measurements at different depths and extrapolate it to 0 depth to get this coating only value of stiffness. But what you're seeing in this, again, I'll find the thing. If we go back, we see again what we're seeing essentially here is this information that we're seeing on the right is because it's coming averaged over a greater area. So these surface features are that you see that the indents are sufficiently small that the plastic stress field is remaining within those surface features a little bit more smeared out. So all of that is assuming that these materials are behaving in an elastoplastic manner. So biomaterials typically are less, it doesn't do this quite as much, to say the least. So they have time-dependent deformation, viscoelastic, viscoplastic deformation. So this is actually not a biomaterial. This is a polyester. And we've just got a couple of examples there where the only difference, indents at different positions, is the differences in the amount of hold at peak load before we're unloading. And the red curve, you can see this so-called nose or bow during unloading. And if you try and apply standard elastic unloading analysis to this, you don't get a sensible elastic modulus measurement at all. However, if you apply the same analysis after a sufficient hold period, then you can get reliable numbers. There's an example there from National Physical Lab a while ago. So this again, so you can improve things by the increased hold together with a fast unload rate. And this is mentioned in ISO a little bit. So they talk a little bit about how you can use to design, particularly for soft metals, but the same sort of things apply very much for polymers, that you want to have this relationship where the unloading rate is sufficiently, is greater than 10 times the creep rate of the peak load divided by 1 over the stiffness. And if you do that, then that means that the effect of creep on your unloading elastic modulus measurements is minimized and you can get a reliable value. So an example of this sort of thing in practice, this is going back quite a while for a little study on some polymeric nanocomposites. And here you can see there's a load time and load protocol of something like 300 seconds or so. And most of the test is a hold at peak load, and there's an additional hold at 90% unloading. And this is not for thermal drift correction. This is for looking at creep recovery. So it's very difficult to separate out for highly viscoelastic materials the effects of creep and thermal drift, creep recovery and thermal drift. So really, you do need it's preferable to have a low drift instrument like the nanotest to do these tests rather than try and correct things out. So if we take this experimental protocol and we apply it to nanocomposites or polymeric nanocomposites. So if we think about a nanocomposite, it has lots of useful properties, and you have a polymer matrix, but you might want to improve its creep resistance and stiffness. And one of the ways that that's commonly done is by introducing fillers. And in this case, we're seeing rather schematically again that a conventional filler, in this case it's sort of illustrated for clay tactoids, is shown there on the left essentially. So you're getting some polymer chains, there's some breakup of the structure, but no, there's not much breakup, and most of those polymer chains are basically not affected by that filler. So you can put quite a lot of filler in there and it's not doing so much for you. If you intercalate, you can increase the gallery distance within the clays, and then you can put polymer chains within there. That's quite a good strategy, and you in practice has shown that you get even bigger improvements for exfoliated structures. So a lot of polymer and their composite design is based around trying to optimize for these intercalated and exfoliated structures. So we have an example here, again from quite a while ago, where there is a nylon 6 thermoplastic, which has then been modified with sub-micro composites and nano composites, and you can see on the left there they do change the curves a little bit. They change the creep resistance, they change the unloading slope, but it's not immediately obvious from those curves. It looks a bit of a mess. When you crunch the numbers on the right, you can see straight away that for a given filler loading, that the nanocomposite route is better. So that's implying better filler matrix interactions. But equally, you can see the increases are relatively modest. So you have for 20% filler loading of clay, which is a much stiffer material than the polymer, you're only getting sort of doubling or so of the stiffness. So what's going on? So why is what's really behind, apart from sort of quantitatively saying that the nano is better? Well, it turns out you can use the advantage of having had that long hold period in the experiment and say, rather than this creep being a headache that affects the accuracy of the unloading measurements unless you account for it, we actually say it's actually a useful thing in itself to look at and study. So here we're able to apply some simple analysis we developed to look at time constants in this case. And what you can see is that the time constant for the submicron composite essentially is not being affected by the filler loading, whereas on the nanocomposite it is significantly altered. So this is telling you again that there's a beneficial constraining influence on polymer chain constraint in one system but not the other. Okay, so this works. I've forgotten this wasn't coming up as a thing, but on the left we get there are 4 curves again on the thermoplastic, in this case again nylon 6 in this case, and it's mechanically homogeneous material, and yet there's quite a difference. What's happening is that in fact that the test environment has been changed between doing those different indents, and what's happened, and it's been changed by using a small volume humidity cell that we have as an option in the nanotest that one of my colleagues Adrian developed. This allows a small volume to be rapidly changed, and nylon essentially is plasticized by small organics and also by water molecules. So if you want to design this type of test, you need to, the best way to do it is to dry it out and then introduce humidity, moisture into that cell gradually rather than try and do it the other way around, because studies have shown it takes the best part of 10 times longer to get the water out than it does to get the water in. So you can study these things. What we can see as well with this application is that there is enhanced stiffness for this the nanocomposite over the virgin polymer, but also that improvement in stiffness as a percentage is much better at these high humidities. So that's useful for design purposes again. So we talk about, again, that was sort of background on the test methodology. So this methodology has been applied to look at various different biological applications. So here's one, this is a courtesy again of Professor Jason Zhang and his team in the soft matter engineering group at the University of Birmingham here in the UK. And Jason's group were particularly looking at bone tissue engineered scaffolds, and particularly how they could design the hydrogels in as part of those scaffolds. And hydrogels, as you can see, have many very useful biocompatible properties. However, the challenge is twofold. One is that they're not particularly stiff, and two is that they're time dependent deformation. So what Jason's group were looking at was ways of improving on the properties of these hydrogels. So they took this microfilabrated cellulose, where you break up the structure of the cellulose fibers and you increase the surface area, and then you allow it to have much more opportunity for hydrogen bonds. And then you create these ionic covalent entanglement networks in between this in this hydrogel of methacrylated gelatin and sodium alginate. And you can see that structure he's got there, and then his group, as part of this multi-phase study, they've looked at the mechanical compression, but also the small-scale mechanical properties to have a better understanding of what's going on in terms of the subtleties of the process. So what they found here is in agreement actually with macroscale compression data, is that that putting these nano filabrated cellulose or the microfilabrated cellulose increases the stiffness of the composite. It also changes the distribution a little bit, but it's somewhere in between those it's less successful. So it's interesting to sort of find out why, and we can dig behind that a little bit. Well, also before I talk about that, and again, he's talking a little bit about different enhancements coming from the cellulose fibers themselves, from synergy between the cellulose fibers and the ionic covalent entanglement networks, and also between the two things. So hardness is slightly less useful parameter than modulus for these things, but more information is again found through looking at the time-dependent deformation. So we're applying a similar model here, and what we're seeing, if you look at the left there, is we're seeing that the without the cellulose in there, that hydrogel is susceptible to creep. If you put some nano filabrated cellulose into that, it improves things, and if you put more micro filabrated cellulose into that, it improves the creep resistance more and more and more, which is a very useful design improvement thing. And Jason wondered why that was, and he did some surface science measurements on there. So there's measurements of zeta potential there, and you can see there essentially that the nanofilabrated cellulose is essentially it's at the point where you're getting some agglomeration, which is not helping, but there's more stability with the much bigger and stiffer microchains. So there's a little summary of what Jason put about this work. Apart from getting into these improved materials, they're understanding fundamentally how these materials work. I should have said a little bit more about the time dependency and how the hydrogen bonding is being affecting that essentially. So all useful stuff, but very much within the bounds of quasi-static testing. So nanoindentation is a so-called quasi-static test technique. In many real-world processes, including biological samples, the impacts are they're involving high strain rate process. So impact is really more important. So we can generate these impact tests, these high strain rate tests in the nanotest, and there's a schematic of it shown there. We can pull the probe off the surface and fire it in under these to generate these high strain rate indentation tests or impact tests. And if we want to, we can go backwards and forwards and look at cyclic tests. So one of the first situations where this type of thing was done on biological samples was at MIT, when they were looking at trying to simulate the damping response of different polymeric systems and try and match that damping response to various tissues as part of a developing armor for the US military, essentially. So in this case, they've got these are very soft samples being impacted through liquid, and these are essentially so rather than these very small diamond probes, now we're getting a small, a few millimeter spherical probe, and you can achieve some quite high densities with this testing. More recently, also out of the US, is some work done at UC Riverside and by Professor David Casalis and his team there. And they were looking particularly at the dactyl club of the mantis shrimp. So in its operation, it's subject to many thousands of impacts, and to get it its food. How does this work? And they noticed that it's got this hierarchical nano or micro level structure with different reinforcement and different length scales, and they're trying to sort of understand why. And part of that work, they were doing some small scale impact tests. In this case, they used a range of different test probes. Sorry, for sharp cube corner diamond indenters, also small spheres. They generate these high strain rates for the test, so these are much higher than you can achieve in normal nano indentation, where you're maybe limited to sort of 10 to the 1 to the -1 per second is more common, and typically you're acting at much lower strain rates to get that quasi-static contact. So you can see, if you look on the right, the example there of a multiple impact test, and there you can see that different parts of that structure will have completely different impact behavior. So the initial damage is rather similar, but then with multiple impacts, you can see there's very clear differences in terms of how these structures behave. And there's different deformation mechanisms that you see in impact that you don't see in quasi-static testing. So a few years ago now, that group relocated to UC Irvine, also in California, and continued their work developing understanding for developing resilient multifunctional materials. And particularly, they were interested in sort of for coating systems, how could they balance hardness and toughness to most effectively dissipate impact energy. So there's a couple of references there. The pictures are taken from the one on the top. And what you can see there is chitosan is essentially been, there's a composite there. You put silicon carbide into that, and as you increase that fraction of silicon carbide in that composite, you rather dramatically change its impact performance, and you can see this maximum sort of the more localized impact damage in those cases, E and F, as you see there, and even sort of, but so it's either those two or maybe even the G system, where you say, well, actually it's a little bit more damage, but it's no cracking. So all of that sort of useful information, they can understand how to build in these dissipative mechanisms into their coating systems. So this, moving on to the tribological part of the tests, essentially. So if we think about tribology, a lot of tribological testing is done at a more macro scale, where there is essentially high pressure contacts between the asperities. What you're seeing is that the assumption in something like a pin-on disc test is that you can calculate an apparent contact pressure, and that is the contact pressure. But if you zoom right in, as there's this very nice example, somewhat famous paper here by Kathy Barlow and Greg Sawyer, where they show that real area of contact is initially a tiny fraction of the actual area of contact. And there's been some very nice experiments done quite a long time ago now, where people have looked at transparent surfaces essentially, and the contact between sliding transparent surfaces as a function of load, and you can see just how much of the material is in true contact, and when it's not in contact, the light is scattered, so you have a very clear metric in terms of how much is in contact. So we call these type of tests, we can call them perhaps nanotribological tests, but generically I would say single asperity tribology is essentially what we're talking about. So nano and microscale tests are particularly useful. We can do a lot of these type of tests in the nanotest vantage system. We have lots of scratch tests, we have some fretting tests, we have some reciprocating tests. All of these things build into that type of contact. So if we think about systems in general, biological systems, fully lubricated contacts are the ideal. So with low clearances. So a lot of people are going to design these things on the assumption that you have this fully lubricated contact. But in fact, when you look at explants, essentially, so as you see on the right, then you get very, very small scratches, often cross scratches that you see on the surface of failed hip joints. And particularly when these things wear out much more quickly than they're expected to. So there's lots of different ways to design this system, and there's a lot of work going on where the small scale tests are really helping inform the materials choice and the alloy development choice by replicating these in vivo conditions and understanding these damage mechanisms better. So here's a simple example from the University of Birmingham now. So here they are looking at cobalt chrome alloy, and they're looking at reciprocating wear of this in a phosphate buffer solution, sliding over 1.5 millimeters, and then essentially seeing what happens. So this is Mike Bryant's group now at University of Birmingham. So first of all, you can see on the unmodified surface here, you can mechanically map that unmodified surface, and you can see it has a fairly tight hardness distribution. So it's very hard for a biomaterial alloy cobalt chrome. So these are fairly sort of typical values, sort of just over 5 GPa. And after the wear tests, so after the tribological tests, they've then sectioned through that, and you can see that microstructure that you see on the left has now evolved into a much finer microstructure just under the surface. So you're having this recrystallized layer, tribologically transformed structure, if you like, and this has altered mechanical properties. And as you can see bottom right there, you can see how they've been, that group there, a different group in Birmingham, they've been looking at how that changes in terms of contact pressure and layer thickness. And this was interesting because they found some neat work where they're showing that how this microstructure correlates with the size and morphology of the debris. That is one of the issues in these systems, is how this evolves. So similarly to this is some work now from quite a number of years ago now in the NCATS in the UK, down in Southampton. So here, Sundan was doing some work, in this case looking at scratching in, again, simulated body fluid, and performing the scratches to at sufficiently high load that she could remove the native oxide. There you see a couple of examples there, and different load levels, creating different scratches. And from one of those tests, you can see on the right that passivation layer is removed. When it's removed, it releases these metal ions. This is one of the mechanisms. This, as part of this sort of aseptic loosening, this metal ion release is considered to be one of the headaches to try and avoid and design alloys around to mitigate this problem in joint design. And it's interesting that, as you can see there, so the tribological tests that you can do in the nanotest system, that you can see there's quite a while, it takes quite a while before this system calms back down and it's repassivated. So again, you can compare this type of thing against different alloys and design the one that has the best resistance to depassivation and the quickest time to repassivation. So the work we did in conjunction with Thomas Liskowitz quite a while ago now was in looking at small-scale fretting of alloys, and there we were able to correlate with things like the H/E ratio in the material, and then looking at different load levels. And we could see in this example that the material, the titanium 6-4 particularly does well at the lowest forces. It has this highest H³/E², so it has this highest. It has the highest load carrying capacity of these different materials at these small scale. But then as you go on, then it has this, once you're breaking that structure, then you have this quite severe damage that you can see in that H there, and you're getting this sort of delamination type wear, which is detrimental. So that sort of thing is typically a problem with titanium alloys in these biological applications. They're quite sticky, which doesn't help. More recently, we haven't published this yet, but we've been looking at small-scale reciprocating wear tests. And now we have designed as reciprocating wear tests, so we can look at friction and depth, cycle by cycle in these tests, quantitatively, all corrected for any thermal drift that might be happening. And there you can see just an example of, sorry, it hasn't come out that well, but how the friction changes its polishing out on the 316 and the cobalt chrome, and it's initially very high on the titanium 6-4 and also on the titanium grade 9 that you see on the left, and that's accompanied with more wear until eventually removing that. So in those type of scratch tests or in the reciprocating tests, all of the contacts are at the same point. So you're going backwards and forwards in the same track, which is, it doesn't exactly match what's happening in the body. And one of the things that we've been looking at is to simulate abrasion more generally by having computer controlled spatial distribution of scratches. And this is an example from an ongoing project with Tom Slatter at Loughborough here in the UK. And what we can see on the example there on the right is that the top two is showing 20 cycles and there's a change in load. So as we change the load from 10 millinewtons under these conditions to 50 millinewtons, we're getting a transition from top left, you'll see that set of 4, you're seeing hardly any damage, to suddenly you're getting this much more damage and this debris, and that's due to a transition in the attack angle. So there's promotion of this transition to cutting at lower angles when you have these multiple structures, when you have residual stress fields and pile-up affected previous scratches. So it's a much better test. It's in many ways, it's a much more reliable and useful test than just doing scratches in the same position. And again, you can see that on the bottom two, you can see if we're comparing, say, 10 millinewton at 20 cycles and 100 cycles, you can see it's not just the load. You can run that on, and you're getting that transition to these more damage regimes. You get load dependent deformation. You also get a number of cycles deformation. You get this debris. So we've had some interesting results, particularly for additive manufactured applications that we're working on. So it's quite a nice correlation between performance of this test and the performance in the G65 abrasive test. So hopefully that was a bit quick, but gives you some idea of some of the potential of using nanomechanics as a test technique to study these links between structure, properties, and performance at very small scales under the right environmental conditions, and really providing the sort of information you're not able to get by other test techniques, and then using that to develop better understanding, better wear-resistant materials, not just for biological applications. Okay, the acknowledgements, the guys, most of them I mentioned on the right. But thanks very much for them for providing slides and useful interactions as well. So thank you for these guys. Thanks, and that's it for now. Thanks. Thanks, Sam.
Okay, brilliant. Thank you very much, Ben. We'll swap over the other slides in a moment. Just to highlight for anyone, of course, if you have any questions on instrumentation, which Ben will be talking about a little more in a moment, but also any of the content or anything else kind of on nanomechanics, please go ahead and type those questions in the chat. We'll just swap the slides over. There we go. I'll let you talk about the strategic partnership with Artec now. And
right. Thank you very much. So yes. So Micromaterials have been our own company for a very long time, but we've had the opportunity to join up with Artec Instruments in the last few months. And this is really exciting. There's a strategic partnership where we have the opportunity to bring the knowledge base and complementary expertise in the two companies together, really as a driver for accelerated growth. So Artec Instruments as a group have been around an awful long time. We've been very impressed with them. And this is actually a snapshot that I took of presentation by Philippe at Artec a couple of years ago. And this as just showing of all the test instrumentation that they had at the time across the different tribological tests. And you can see there you have a multifunctional tribolometer, the MFT 5000, typically the top range thing, but a range of other things such as the vacuum testing, high pressure testing, some fretting tests, and also going into the scratch and indentation arena as well. So that was in 2024, but if we go forward now for a couple of years, and you can see this range is expanding quite considerably. So now there is an air jet erosion tester, there's chemomechanical polishing added to the range, there's a range of 3D optical profilometry tools. A lot of these things, these can be integrated with the different indentation and other test techniques. So that's a unique offering that Artec have, is this ability to integrate 3D profilometry with this optical 3D profilometry with their indentation systems. And they have a range of other different developments. And that's just Vantage and Extreme systems. You can see one of them there. There's the Vantage sitting there on the right in the product range, as we've joined that indentation group now. So watch this space for new developments. So we are actively working with them on the technological side, also on the person side, but also if you can't quite wait that long, please join us, because we're both going to be in Nordtrip in a couple of weeks' time, or less than a couple of weeks' time now, I guess, in Finland. And so Philippe and I have some talks, and then obviously further things after that. But anyway, so exciting times, and just thought I'd introduce you to Artec. I know you've all heard a lot about them in other surface venture things over the year. So now we're part of the Artec group. Okay, that was it. Short and sweet. Sam's escaped. No, he's back.
Just take a moment to come back on stage. Thanks, Ben. There we go. Okay, so we'll get to the Q&A in a moment. I just noticed a comment there in the chat. Warren, if there's specific acronyms you weren't, if you can remember what they were, or sort of, we're here to answer questions. So please do go ahead and let us know what those might be. Slides off for now. So before we dive into questions, let me just release the attendance certificate, which is down in the bottom left. there. So we have one there, just a quick one from Warren before we get to the other questions. Just is AM additive manufacturing?
Yes, it was. Yeah.
Yes.
Hmm.
Yeah, it is. Don't always see that one. It does tend to get used a reasonable bit. So, but right. We have a couple of questions in the chat right now. Please, if anyone else has any other questions, please type them in. The attendance certificate is there. It is going to be active for the next day. So don't leave us just yet. Click the link, open it, come back. We've still got plenty more to talk about. So we've got a first question here from, excuse me if I'm mispronouncing this, Abdulrahman. I hope I've said that correctly. Who asks, were all the tests done using the same machine?
Effectively, yes, is the answer to that. Though the one of the University of Birmingham, the tribological tests that they then did the indentation with Arensmon, that was done on a different instrument, but it could have been done on a nanotest with the tribocorrosion cell. So that certainly could have been done on a nanotest as well. So essentially the answer is yes, all of the tests were done, because the nanotest is a multifunctional instrument, so it has the capability to do all of these different tests. So customers pick and choose which modules they want, and so they matches their applications, and they don't pay for things they don't need, things like that.
Thanks, Ben. We have another one here from Ario. Again, apologies if I'm mispronouncing. Said, could this approach be used in a multi-layer material, i.e. zeolite, for observing its microstructural defects? Since my research is related to zeolite or CO2 entrapment, I presume that may be the nanomechanical mapping, or just the, say the impact wear, perhaps?
There's a lot of things going on with zeolites that could be of interest. I think scratch resistance certainly is something that's affected by the microstructure quite heavily in zeolites. So I didn't really talk about it, but the advantage of the scratch type testing is you can tune the test capabilities. So you don't need to overdo don't need to drive it to failure straight away. This is one of the advantages of being able to have a tightly controlled system that you can tune the load and the depth exactly as you want, essentially. But of course, I mean, equally, there could be a bunch of things. I mean, there are, difficult to say really. There's a lot of things that could be done.
Yes, yeah, definitely lots of possibilities there. I think we can tell about a question that must have been, I think I may have been the sort of when you were talking about both the impact and scratch. So it's I think kind of one of the things to perhaps highlight, if I done with the the nanotests, the nice thing is the sample mounting is very open. You can, well, I think you can talk about it far better than I, but in terms of different samples, there's the possibilities are certainly there.
Yeah, I mean, excuse me. Sorry about that. Of course, you can, if you have a relatively small samples, you can map many samples together and test all of them together. It allows you to build up quite a picture of what's going on quite quickly. So that's, from a throughput point of view, it's certainly a useful tool for that type of thing. So multiple samples, set all the tests up together. It can run 24/7.
Yeah, very happy with that. It was good to sometimes run at night when there's not going to be any vibrations around or anything like that if it's a particularly sensitive thing, which was one of the things I used to do. One of the questions I have, Ben, just whilst we're waiting to see if there's going to be any more from anyone in the chat, in terms of the mechanical property maps, what sort of resolution are you able to get with those, and what is the typical time taken to actually achieve one of those property maps?
I mean, those 1600 indent ones are a few hours for sure, but the resolution is designed not by is to some extent probe geometry defined. So you have to think about the stress fields you're creating. So you can go towards very sharp probes. It also puts a challenge then on how much time you are prepared to put into surface preparation. So yeah, people certainly have, I've seen things where people say, oh, there's 100,000 indents. Oh, yes, it's 100,000 indents, but it took you 2 days to prepare your sample. So, so there's different things that you can get out of these things. So, if you think about that one I showed about the high temperature map where they're 80 nanometers deep. So we spaced them 1 micron apart, and so if we'd have spaced them any closer, then if you think about the geometry of the indenter and the plastic stress field, they start to interfere. So it's a geometry of the probe that limits rather than instrumentation or anything else. We didn't talk at all about impact mapping, but that's another thing that can be done. So we can do, and somebody was asking me about this the other day, and I did vaguely remember that we did something along those lines an awful long time ago for biological samples.
Yeah, and perhaps another thing to highlight as well, though it's not really a key focus of this talk with the biomaterials, but the I think I'm right in saying is randomized impact and scratch. Is that the terminology settled on?
Well, we used. I think possibly the problem with randomized suggests that it's somehow not controlled. But in fact, what we're doing is we're trying to replicate the random impact or the spatial distribution of impacts that might occur on a surface subject to erosive wear. So we have abilities to use to computer control statistical distributions that we then can save and restore and reuse at different load levels or different samples. So then it's spatially distributed, I think is possibly a better word, but we're learning on these, what we should call these things.
Yeah. But yeah, really good capability. I mean, it was obviously it's there for the scratch, but it's also, as well, you can either select the area of the more spatially distributed. We do have another question from Harris, who has asked, are there any models available for modeling friction using a Berkovich tip? I've seen people using contact mechanics for a conical tip.
Yeah, there are. And it's in that case, you need to be aware of whether you're scratching edge on or face on, because that makes a difference to how much ploughing contribution you have, and you can calculate that out. So we've done that for hard coatings and seen clear correlation. So you have a ploughing component, and additionally you have some interfacial component, and what you measure then as a function of load is a combination of those two things. And we've found some success correlating that against mechanical properties, because then the ploughing contribution is lower for the higher H/E type materials. You can see that sort of thing. But basically, yeah, it does show that you are super sensitive to the amount of ploughing, and then but basically you get up to a certain level where I forget exactly what it is, but it varies between edge on and face on.
Yeah. I mean, are there many people that just sort of expanding on Harris's question, are there many people that do any kind of friction sort of scanning type testing?
It's a risky thing, because it depends what you're scratching. So if you think about one of the advantages of a sphere is it's more likely to not be damaged. And if you think about a super sharp Berkovich, if you scratch with it, then maybe it's not super sharp. So in most of what we've done, probes have been sufficiently blunted before we've done scratches with Berkoviches, or we typically go towards directly small spherical probes. That seems to be a useful way to look at it. So not many is the answer. I think sometimes you saw a bit of it because some instruments years and years ago, they used to glue in the probe, and they use their own, not our instruments, but other manufacturers, and they had no choice to take the probe out, so they had to use that probe. But it's not super clever, if you ask me.
Yeah. Always easier to be able to change the probe depending on what
It
the test
is, yeah, and it's one of those nice things in that test that changing the probe takes, as you know, Sam, takes a tiny amount of time.
Yeah, it's very quick. One of those nice things. Thinking about probe changing and just sort of thinking back to just what we were talking about as well with the indentation mapping. Does it have you done much, or has anyone done much with, say, a cube corner where it's a lot sharper to get better spatial resolution? I know you said obviously yes, you do a particularly sharp Berkovich, but I wonder if there's been much with, say, a cube corner.
Yeah, I think, yeah, cube corner is sort of, I think that there is occasionally you do see that, you do see cube corner maps, yeah, for that reason. I think if people are trying to get closer. But again, it depends what you're testing. You've got to have that certain level of, well, let's put it like this: if you're testing a soft alloy or something, then it's not going to be a problem. But if you're starting to test even something like a cemented carbide or something, I think, or anything harder than that, I think you'd start to have problems if you're trying to do very, very small indents, because then your geometry is going to potentially change. I think this is the issue, is that the probes naturally wear down to a point at which they may or may not wear much more, and then they can be used in these maps. But if you start off with a super sharp one, then it's something to be aware of in high temperature testing as well. You don't necessarily want to do all of your tests with super duper sharp tips.
Yeah, absolutely. Actually, a good question as well from Harris there, just to sort of clarify the differences between the different geometries. Thanks for the question. He said, I've also seen different Berkovich probes, like I saw a paper of yours, I presume that must be yours, Ben, using a 1 micron probe. How are these different, as they're all pyramidal, particularly where high loads are applied?
Oh, well, okay. So I suppose that in that sense, it's kind of what I'm describing, is that it was a very sharp Berkovich indenter that probably, you know, was used for a long time for a nano indentation. At some point, it gets retired from nano indentation and used as a scratch probe. And at that point, we've done a set of indentations into a reference sample like pure silica. We've determined what the end radius is, and then you'd probably define it as a blunted Berkovich, or it's a spheroconical probe. So Berkovich has an effective semicone angle of something like 70 degrees or something. It's not exactly that, but for contact mechanics mode, it's about 70 degrees. So you can kind of model it that way as well. So you have two options. So people do similarly when they talk about conical probes. All conical probes that people want, you know, they're going to have some end radius. You see that at a bigger scale, people often talk, they don't necessarily own up to what that radius is, but they're clearly having some end radius. Yeah, that's a good point.
No, that's great. Thanks for the question.
So and back to the comment there, when high loads are applied. Well, yeah, the tip defect becomes less and less important the deeper you go. That's just. But if it starts off as a micron, then it's still appreciable. But you're often in a how do I put it? Spheroconical contact, not dominated by one or the other situation. So it's not, you can't necessarily eliminate one and just say, this is only a conical contact, or this is only a spherical contact, or this only there's going to be some combination of the two. That's from my memory of friction. I think it is that with these blunted probes.
Yeah, it just depends on how much of essentially for what the load is, how deep you go, to how essentially how
exactly. I suppose that's it, isn't it? Yeah. So exactly that, compared to that sphere cone transition depth, where are those the the depths, the penetration depths in your test related to that.
Yes. Okay.
Which will be fun to find out at a later date. Yeah.
Yes. Okay, so I think we're at our 60-minute mark. I just want to do a final call for any final burning questions that anyone may have. Otherwise, we can just wait for a few seconds just to let anyone type. Yes, it doesn't look like we have anything else. So I think with that, it's now a good time to bring the event to a close. So thank you very much, Ben, for the great talk and for telling us more about the strategic partnership with Artec, which is very interesting. I'm looking forward to seeing what happens there. Thank you very much to Micromaterials for the support for this event, as always, and as I always say, we wouldn't be able to do it without our partners. So thank you very much to them. Please, everyone, do go take a look at the Micromaterials website and their LinkedIn page. Great resources for a lot of technical information, not just yes, there's there's promotion for conferences and whatnot, but a great amount of technical details or references to papers that would be really good to go and read. So please go take a look at that as well. Please do take a look at the Surface Ventures website. We have our archive of previous talks all available, some of the on-demand ones. And do take a look at our LinkedIn page as well, announcements for events upcoming. We will as well be looking to organize an event in June. However, we do have the event site for our July keynote available in partnership with Droplet Labs. So if you are interested in that, please do go ahead and click on the registration link down in the bottom left. We'll be updating the website and updating you all on LinkedIn and via email what will be happening there. But with that, thank you all very much, the audience, for being here, for setting such great questions. And finally, just to say, if you enjoyed this, please do take a little bit of time to advertise this event to your colleagues, your friends, anyone you think would be interested. We'd love to keep growing and doing, spreading what we do to more people. So thank you all very much.
And thanks very much to Sam for hosting as usual. Much appreciated. And thanks to the audience. And we'll say at that point, I'll say goodbye. Thanks. Cheers.
Thanks. Thank you. Thanks, Ben. Bye.